We will discuss two methods, one with the aircraft under pressure and the other without pressure. In the first example, we will pressurize the cabin using either aircraft engines or the auxiliary power unit. UE Systems' warble tone generator is placed inside the aircraft and ultrasound is transmitted. The shortwave ultrasound signal deflects off solid surfaces but will find and escape through a leak site. By scanning the exterior surfaces of the aircraft with the ultraprobe, you will hear a leak, which will also show up on the ultraprobe's meter. To do this, use the ultraprobe's scanning module and follow the intensity of the signal to its source. We call this method of zeroing in on a leak site the gross to fine method. To pick up gross signals, set the sensitivity level at maximum, or 10, and use the fixed band mode. As you scan large general areas of the aircraft, listen for the tone generator's warbling sounds. Use the rubber focusing probe to narrow the field and reduce the sensitivity to pick up only very fine ultrasonic signals. Recognizing the sounds of leaks comes easily with practice and is also made easier by watching the ultraprobe's meter as it responds to varying signal strengths. Confirm the leak by moving the probe back and forth over the site. Although each tone generator fills up to 4,000 cubic feet, the basic structure of an aircraft hull tends to reduce the ultrasound intensity. Therefore, in some situations, it is recommended that you work with a partner inside. Have your partner move the tone generator every 10 feet or so as you scan the outside. For larger aircraft, more tone generators may be needed. For very small leaks or where there is thick gasketing and insulation, the tone generator should be closer to the test area. If there are loud shop sounds nearby or jet engines in use, it may be easier to use the tone generator outside the aircraft and scan from the inside. Most often it's desirable to pressurize aircraft enough for gaskets to create a proper seal around the doors. Refer to the appropriate service manual for the aircraft. If it is not possible to pressurize the aircraft, the test may still be conducted. The procedure is basically the same as we've just described. Place the tone generator inside the cabin, set the ultraprobe to log, and use it in the fixed band position. Insert the rubber focusing probe and scan a test area. Since the gaskets will not conform around the door seal as they will during flight, there will be some normal acceptable sound penetration. To distinguish these sounds from those of a leak site when testing, start by noting the sound levels of doors known to be in good operating condition. Use these normal sound levels as your basis of comparison for future testing. It also may not be necessary to pressurize the craft if you're just checking for leakage around windows. To find the leak in the seal of this cockpit window, we aim the tone generator at the window and use the same scanning method from inside the airplane. Next, we'll show you how to use the ultraprobe to inspect fuel cells. To check a wet fuel cell for leakage, the tank is drained and pressurized with air or nitrogen. There must be a minimum of 2 to 5 psi within the cell for the test to be accurate. We then scan following the rushing sound. In certain cases, you may hear a crackling sound from residual fuel in the tank as it is forced through the leak hole. Now let's look at how to inspect dry fuel cells. Although you can use the method we just demonstrated as an alternative, the method of choice for dry cells is the tone generator method. For large fuel cells, it is preferable for one person to scan from inside while another holds the tone generator where needed on the outside. For small cells, the tone generator is placed inside the cell and you scan the exterior. Again, the gross to fine method is used to close in on the leak site. The ultraprobe is set at maximum sensitivity and is in the fixed band mode. The rubber probe is attached to block out unwanted sounds. As we get closer, we reduce the sensitivity. We can also check the meter's response, and then we confirm the leak site. A technique we use for very small leaks in either wet or dry fuel cells is liquid leak amplification. The cell must be pressurized for this method. The liquid leak amplifier is a low surface tension liquid. Poured over a suspected leak site in small amounts, it forms bubbles that will collapse, creating ultrasound detectable with the scanning module. Apply the liquid leak amplifier to the test area and listen for these distinctive sounds using the same gross to fine scanning method. Next, you will see how the ultraprobe can be used to check any pressure or vacuum leaks, such as might be found in pneumatic systems, oxygen systems, and other pressurized gas systems. You will also see how it is used to check tire retention. Regardless of the location of the leak, it will produce a turbulent flow as escaping gas moves from the high pressure side of the leak to the low pressure side. Once you become familiar with the sound quality of the different types of leaks in your environment, you can easily locate a leak. This is the sound of a pressure leak as heard through the ultraprobe. The leak detection procedure is the same as was used to locate the sounds of the tone generator. To pick up gross signals, begin scanning with the sensitivity set at maximum and use the fixed band mode. The meter mode should be in the log position. Scan the area following the characteristic rushing sound. Use the rubber probe, reduce the sensitivity, and listen. Watch the meter's response and confirm the leak site. If a noisy environment presents a problem, various shielding techniques can be used effectively to block out competing sounds. The rubber probe can be used to deflect the unwanted sounds. Or changing the angle of the ultraprobe may help. You may be able to use your body or cupped hand to block out competing sounds. Even an object such as a clipboard may be used. The wipe rag technique for blocking unwanted sounds can be particularly useful. For yet another method, change the frequency tuning to about 40 kilohertz. Then tune in the exact frequency using the sniff technique and scan again. If a leak is behind a panel, only gross signals will be heard. Check for leakage whose signals may be blocked. Some panels must be removed before scanning is completed. You need not remove all the panels, however. You can find the direction of the leak location by following the sound intensity and removing panels as necessary. Because mechanics can check equipment from a safe distance, the ultraprobe minimizes the risk of being burned while testing hot sections of pneumatic duct. De-icers may also be checked for leakage. Crew oxygen system leakage can be checked by just scanning or by using the liquid leak amplifier method described earlier. Tires are also scanned using the detector with earphones. Point the ultraprobe at the tire and go around the inside of the rim. Also check fuses, seals, and seams. Again, for very small leaks, it may be necessary to use liquid leak amplifier. Ultrasonic warning signals can also be effective in checking hydraulic and mechanical systems. They can indicate a potential problem before it could be detected by heat sensing or by vibration instruments. For this type of testing and troubleshooting, the ultraprobe is used with the contact probe. The contact probe is used to check pumps for cavitation, to check the direction of blow-by in a two-way valve, to detect and pinpoint bypassing check valves in hydraulic systems, and to internally check anything mechanical such as gears, motors, pumps, and bearings. For example, this is the rushing sound of a good bearing as heard through the ultraprobe's headphones. Crackling sounds indicate bearing failure. And rushing sounds, which are loud and rough, can indicate a lack of lubrication. The ultraprobe can be used in the same way as a most effective tool in all general mechanical monitoring and troubleshooting. The same method is also used to check for internal bypassing in valves and actuators of hydraulic systems. Although different aircraft have their own unique systems, the same basic procedures can be applied. Whether you need to troubleshoot the hydraulic valves and actuators for a braking system or a steering dampener, flight controls, or landing gears, the problem can be located with the contact probe. To demonstrate, we're going to investigate the internal conditions of this hydraulic valve. The fixed band is used, and the meter selection dial is set to log. Because the sensitivity must be adjusted according to a normal operational valve, a couple of good valves are tested, and a standard is developed. Then the valve is compared to the standard. It's a good idea to maintain a history of the ultrasonic patterns of all key components of your operating equipment to help in diagnosing problems and prevent downtime. Knowing your equipment and understanding how it operates is a critical first step in recognizing changes in its individual sound character or sonic signature.